And our first speaker is Dr. John Warner of the Warner Babcock Institute for Green Chemistry. His presentation will be Green Chemistry and Commercial Applications. Dr. John Warner is a recipient of the 2014 Perkin Medal, widely acknowledged as the highest honor in American industrial chemistry. In 2007, he founded the Warner Babcock Institute for Green Chemistry, LLC, a research organization developing green chemistry technologies, where he serves as President and Chief Technology Officer. Dr. Warner is one of the founders of the fields of green chemistry, co-authoring the defining text, Green Chemistry, Theory and Practice. He holds and has published over 250 patents, papers, and books. His recent work in the fields of pharmaceuticals, personal care products, solar energy, and construction and paving materials are examples of how green chemistry principles can be immediately incorporated into commercially relevant applications. So please welcome Dr. John Warner.
Well, thank you. It's a pleasure to be here to speak with you all. It's a fascinating conference here and a lot of interesting work going on. I'm here today to kind of give you a discussion about green chemistry and how it relates to the industry here. And so I wanted to take a step back and give a little bit of a big picture of the concept of green chemistry and how it all fits together. And so we're in a very polarized society. Obviously, our politics and our sports show just the significance of that polarization. When it comes to materials and the environment, we're certainly equally polarized. You open up the newspaper, turn on the radio, look at the internet, and you hear about this molecule that's bad and this chemistry that's scary and this molecule that's bad and this molecule that's scary and this is dangerous, this is bad, this is deadly, this is killing us, we're dying. And oh my God, everything is coming at us so fast that everything just about seems to be toxic. All right? And so it's almost like that game Whack-A-Mole, the game where the little guy comes up and you hit him in the head. What is the mascot of the American Chemical Society? It's a mole. We're playing Whack-A-Mole with chemicals all the time. Brominated flammatoms, whack. Phthalates, whack. Bisphenol A, whack. And we're exhausted because they're coming at us so fast. And we're trying to wrap our heads around this. Is this serious? Is this really dangerous? Or is this a bunch of hype? I don't. But then the next one comes in, the next one. And we're left kind of breathless, wondering, is this serious? Is this not? And that's the worst part of it, is we don't really understand. We don't know. And I think that what's happened is because, heaven knows, despair sells. The messages that everything is toxic and bad gets out there quite a lot. But I don't think we're asking the right questions. All right. Instead of asking, is this toxic? Is this toxic? We present this. We hear about this as almost like this epic battle of good and evil. You've got industry over here, Darth Vader, that's trying to poison society for profits, and we've got Luke Skywalker over here trying to. And it's just not that simple. It really isn't. And that the issues here are a lot more complicated. But instead of asking, is this toxic, is this dangerous, I think there's a more important question that we should be asking is, why would a chemist make a hazardous material in the first place? Let's take it as a fait accompli that there are red dyes in commerce that cause cancer. Let's accept that there are plasticizers that cause birth defects, that there are monomers that are endocrine disruptors. Let's accept that sometimes this happens. Isn't this a more fundamental question? Why does that happen? So maybe instead of looking at how we make molecules, we should really be looking at how do we make chemists. Now, I'm not a historian or a sociologist or anything like that, but I'm a chemist. Let's look at the path of me becoming a chemist here. So I'm from Quincy, Massachusetts. You can tell by my accent. You can probably tell the street I grew up with if you know accents. But I'm right south of Boston. I went to the University of Massachusetts. I started as a music major and then changed to chemistry and fell in love with chemistry. I actually, I'm first generation. My older brothers didn't go to school. My parents did not value higher education, so I worked construction full-time and paid my own tuition to go to school. UMass at the time was $200 a semester. Those days are gone now, but and got into chemistry pretty hardcore. I found myself next at Princeton, and I became a medicinal chemist. And I worked on a drug called Alimta that is sold by the Eli Lilly company now. It's one of the most successful anti-cancer drugs. And I played a tiny role. There's a lot of other people working on this project. But I assumed I was going into academia and I was going to be a medicinal chemist at a university somewhere. When out of the blue, Polaroid came knocking on the door and offered a job for me to head exploratory research at Polaroid. Now, in the 80s, Bell Labs had kind of gone away, and Polaroid had emerged as the coolest place to be as an organic chemist. I remember at lunch when they offered me this job, I said, "Sir, I'm going into academia, I'm a medicinal chemist." They said, well, told me how much they wanted to pay me. I said, "When do I start?" And I became an industrial chemist, having graduated from high school as class musician. I go to my high school reunions. I'm coming up to my 40th reunion, and when I meet kids that I grew up with, they go, "No, really, what are you?" I'm a chemist. No, really, what are you? And so it's a very strange world. At Polaroid, I came up with this concept called non-covalent derivatization. Now, I'm not going to give you a lecture. If you wanted me to, I could talk for hours and hours on this. I am such a nerd about this subject. The license plate of my car is NCD, so trust me, I could go on and on. But here is the Reader's Digest version. Organizations oftentimes take their employees and have them go out and take a workshop and find what skills they have. I'm good at writing, you're good at data, you're good at this, you're good at this. An unwise organization finds where people are deficient and sends them to a workshop to get better at their deficiencies. I say unwise because if you're not good at something, you're probably hardwired that you don't enjoy it, you don't want to do it. And the things that you do well, you do well because you love it. And a smart organization wants you to do more of what you love and have you collaborate with someone who's doing what you're not good at. And a wise organization puts people together so that they're all passionately doing what they love to do. Simple. I realized at Polaroid, we never thought of that in chemistry. In chemistry, we try to make a molecule, and this part of the molecule makes the color, and this part of the molecule makes the solubility, and this part of the molecule, and we spend all this time trying to make this island of Dr. Moreau molecule. It costs a lot. There's a lot of nastiness going on with that. So I said, why not instead, when you formulate a product, take those different molecules and allow them to collaborate together in an aggregate form and claim intellectual property, file a patent not on the single molecule, but on that self-assembled aggregate. And so non-covalent derivatization is collaborative aggregates, all right? And so I really got into this, and we were lucky that a lot of my inventions went to products. And so Polaroid started to set up some large-scale manufacturing for this stuff. One of them was a way of dissolving molecules in a multi-layered film. Now, as everyone in this room knows, you can't just go and manufacture something. You have to get EPA approval. So back in the 80s, we had to file the TSCA documents, low volume exemption, pre-manufacturing notification. It's interesting. So I had to testify to Congress, both the House and the Senate, for the recent round of TSCA reform. And what people don't fully appreciate is that if you were to take an amnesia pill and look at the TSCA documentation from decades ago, no one would find it unreasonable. It's actually an excellent document. It's not the letter of the law that's the problem, it's how it's implemented. So we spent all this time rewriting something where we still haven't guaranteed it's going to be implemented anyway, so you got to wonder. But anyways, the EPA rejected our application for this technology, not because of toxicity, not because of environmental impacts. They just didn't understand it. They said, oh, small particles, what does that mean? Molecular complexes, are you high? They didn't know what I was talking about. So Polaroid stuck me on an airplane and sent me down to Washington to give a seminar to the EPA and teach them about non-covalent derivatization. I ended up meeting this guy, Paul Anastas, who was at the head of the Office of Pollution Prevention and Toxics, the branch chief there. I knew this guy. He went to school with me. In fact, I've known him since I was like 11 years old. I was playing in a jazz band with his older brother. There's his older brother, there's me on the keyboard, there's my older brother with awesome hair. And this guy here, If you've ever been to Las Vegas, the big billboards, Legends of Rock, the dude who plays Rod Stewart in Las Vegas is him, which has nothing to do with this talk. I just thought it was kind of cool. So anyways, I could give Paul a dope slap upside the head and say, wait a minute. Polaroid has been doing this with all these solvents and energies and reagents. I've come up with a way of doing it that's aqueous, non-toxic, and because it's different, you're going to give us a hard time. Isn't anything better for the environment going to be different? And if the EPA procedures render it difficult to do anything different, aren't you orthogonal to your very mission? Shouldn't you be promoting that which is good? Now remember, this is like 1989, 1990, 1991. The Pollution Prevention Act hasn't even come out yet. And so here I am saying, shouldn't you instead be promoting that which is good? And I realized that, what does that mean, good? Non-toxic, environmentally benign, less energy, biodegradable, persistent. You came up with a whole list. We realized there was no science to describe that. We in the sciences, we love our subdisciplines, right? There are conferences all over the world that have the tiniest of scope, okay? Somewhere there's a group of people right now discussing the possibility of sentience of belly button lint. You know, we just love to have our disciplines. Back in the late 80s, early 90s, was there a science about how to make things non-toxic, environmentally benign? No. So how do you grow a science that has no journals, that has no textbooks, that has no conferences, that has nothing around it? And then to take it to another level, I started thinking about it. Every year in the United States, we graduate 15,000 undergraduates in chemistry and chemical engineering, 3,000 masters, 3,000 PhDs, every year, just in the United States. In 2004, we turned a corner and more women started becoming chemists than men. Not one university in the country, or in the world for that matter, requires a chemist to know anything about toxicology or environmental impacts to get a degree. Just try it. You go to any university, Google, if I want to be a chemist, what classes do I have to take? You will find not one university. This isn't an epic battle of good and evil. This is just a weird evolution of education that for some reason the only people on the planet who know how to make a new molecule, who are going to make a new composition of matter, have no training in what makes things toxic. It's not that the field doesn't exist. Toxicology exists, environmental mechanisms exist, but the people who make molecules are completely separate from that world. And so I realized we needed to change this. And that is the birth of green chemistry. Green chemistry is not a government policy. Green chemist is not a philosophy. It is a hardcore science of how does one anticipate real-world commercial implications when it's invented. Every company that I'm aware of hires a student out of university. The student gets in a lab and invents something. Everyone gets excited. And then all of a sudden the red flag comes out, oh my God, we can't manufacture this. It's regulated in such a way. It's so expensive because we can't use this reagent. We can't do this. We can't do that. And so hopefully the company has to invent it a second time. Sometimes they do, sometimes they don't. If that scientist on day one understood the real world and understood the commercial realities, maybe they would be more successful and faster time to market. Just think about it. The way publications and journals work, the more obscure, the more expensive, the more rare the material you're working with, the most prestigious journal you're going to get published in as an academic, but it's unlikely to ever see the light of day in the real world. And so we've kind of got our incentives a little bit messed up in chemistry. And so Paul and I, we wrote this book called Green Chemistry Theory and Practice. And had I thought anyone would ever read this book, we would have written a better book. But this one, and I feel like Forrest Gump, because if you pick up the book and you read it, anyone could have written it. Okay, there's nothing earth-shaking, there's nothing brilliant. It's, yep, that makes sense. We just happen to be the people who wrote it at the right time in the right place. And boom, next thing you know, it's been translated into 15 different languages. I've been to over 45 countries, meeting presidents and prime ministers and cutting ribbons and giving talks because, you know, this thing, green chemistry, which anybody could have thought of. All right, there's nothing a big deal. What I'm most proud of, though, is the 12 principles of green chemistry, which is the science that one who is an inventor at the beginning, not after it's been invented and in the product, but before it's invented, the things to consider as you're going to invent something. So it's really the science of invention, not the regulatory side of things, but the inventive side of things. All right, and so for me, the definition of green chemistry is a technology that makes the world less exposed to hazard, okay? It has to work. So yes, there is the requirement that it has some environmental benefit, but that's not nearly enough. It has to also sell. Because if it doesn't sell, we're not solving any problem. So if it's just a journal article, if it's just a talk at a conference, who cares? So it has to have superior performance. It has to have superior cost. So my definition of green chemistry is something that, absent the sustainability narrative, the performance and the cost alone sells it. And then, oh, by the way, here's the environmental benefit. The moment you try to put the environmental benefit in the front and try to guilt people out to use it for whatever reason, or regulate people to use it, that is fundamentally not sustainable, because at the end of the day, something can go wrong. So it's the scientist's job to get back in the lab and meet the performance needs, meet the cost needs, and oh, by the way, it's also environmental. By my definition, that's the only thing that's green chemistry. If it's missing any of them, it's not green chemistry. Right? So one would argue that there are no barriers to adoption of a green chemistry technology. Better performance, better cost, and oh, by the way, better for the environment. So the big hurdle is the invention in the first place. And that's where, and I won't go into it today, but is our university system in science geared to train people to be inventors, or are they geared to train people to publish papers? There is a difference, all right? And we need to think about that in chemistry, not in engineering, but in chemistry. So I left Polaroid after 10 years to tackle academia. So assistant, associate professor, tenure, was chair of the chemistry department, director of biochemistry, professor of plastics engineering, and I started the world's first PhD program in green chemistry. Started giving PhDs in green chemistry. It's everything that's in a normal chemistry program, but added a one-semester class in mechanistic toxicology, added a one-semester class in environmental mechanisms, added a one-semester class in law and policy. Over the next 11 years, I had over 120 students pass through this program. The average time it took for one of those students to get a job in industry, average, 2 days. The longest any student from this program took looking for a job was 7 days, because she turned down the first couple job offers. I've been out of academia for a decade. I'm still getting phone calls from companies, John, you got any more students? Because they can do the job of a chemist really well, but they also have a clue about the barriers to commercialization, these regulatory issues, these toxicity issues, all right? And so, because the way I look at it, of all the products that we have available, every kind of product imaginable, maybe 10% escape somebody's scrutiny. 90% of the stuff out there has someone shaking their fist at, maybe for real important reasons, maybe not, but 90% of everything needs some improvement from a sustainability perspective. If you do a Google search and try to find things in the supply chain that might help, you'll be successful maybe 20% of the time. But today, 2016, I would argue 65% of the technologies haven't been invented yet. This isn't a matter of choice. Companies are not rejecting things for any reason. It's because they haven't been invented. What better time in history to be in material science than now? The world needs our students and us to invent these technologies. But when you imagine the field of sustainability and these starry-eyed people that want to save the world, is chemistry what they think they should be doing? Probably not. Our message is chemistry's the problem, when in fact there is no path to sustainability without going through chemistry, and we need to attract people to these fields because we need to invent it. This isn't about regulation. This is not about marketing and guilting people. This is the fundamentals of invention and innovation that we're talking about here. Companies get this. When my book came out in like 1998, every major company in the country started a green chemistry program. Okay, so they all had them. It was amazing. They had workshops internally, because if you have a nasty and you have a safe, technology costs more to store, to transport, to treat, to dispose. It goes on and on and on and on. Who in their right mind wouldn't want the safer technology? All right, I did this. I went and tallied the environmental regulations imposed by the federal government since Abraham Lincoln's time. not a whole heck of a lot happened. In 1962, the year I was born, Rachel Carson published Silent Spring, and you see the birth of the environmental movement. Each of these 3, 4, 5-letter acronyms are pieces of federal legislation saying if you're working with this, that, or the other thing, you got to make sure it's not getting into the land, the air, and the sea. Now, I'm just a simple chemist, not a mathematician or a statistician, but I see a trend here. All right, the single biggest impediment to commercialization is understanding this. The chief sustainability officer of DuPont gave me this statistic a few years ago. It said our R&D budget is $1 billion a year. Our environmental compliance budget is $1 billion a year. We spend the same amount of money inventing stuff as we do making sure that we're compliant with all these regulations. So the CEO says, from now on, I want all my scientists to only invent non-toxic, environmentally benign, non-regulated stuff. We can save all that. Oh, not one of those scientists have ever had a class in toxicology, have never had a class in environmental mechanisms. They get the need, they just don't have the skill set. And so after it's invented, you can't go back and uninvent and reinvent. It has to happen before, not after. All right? So in 2007, I left academia to start my own invention factory. I met Jim Babcock, and he and I cooked up this plan to invent for the needs of society, focused solely on performance and cost, but offer the sustainability objectives too. We don't publish any papers in journals. We don't speak at technical conferences all that often. We really focus. We have no students writing theses. It was just 30 PhD scientists focused round the clock on just inventing stuff. And it's a Taj Mahal for science. I've been to many universities. This is like anything that a chemistry department at a university would have. It's a 42,000 square foot facility with every piece of equipment you could possibly imagine under one roof. And we make small molecules, we make polymers, we fabricate devices, extrude plastics, make coatings, and then analyze those things. And then that night before we go home, stop making the next iteration. And so we just crank out these inventions. But the toys are fun. It's the people that really make it hot. And so there's, like I said, about 25 scientists that are passionate. They have graduated from world-class universities knowing how to make stuff, but they're also trained in toxicology, law and policy, and environmental mechanisms so that they're not doing the esoteric. They focus on the real. Right? And so we're kind of all over the place. And there's a necessity for doing that. And so I'm just going to give you a snapshot of some of the things that we've done in the last 3 years. We've been in business for 10 years. Okay, so we started in 2007. For the first several years, our model has been what I call contract invention. We're not contract research. A company will come and ask us to invent something. I charge my cost to do the invention. And then when we succeed, then we have some kind of way of profiting. So we put at risk the profits and only focus on the invention on a cost basis. And we've done that probably 60 or 70 companies over the last 7, 8, 9 years. The last 3 years, we've started to do our own stuff. That we just decided instead of going and working with a company, why not invent something that I want to invent? And we've had a blast with that. And we've started 2 daughter companies. We've got a medicinal chemistry, a material science company called Collaborative Aggregates, and we have a medicinal chemistry called Collaborative Medicinal Development. We have, interestingly enough, an Alzheimer's drug that we've been developing, okay? And we've got a bunch of patents on this, and we're trying to push that into clinical trials. Sitting next to the person that's working on Alzheimer's, we have a formaldehyde-free wood composite technology. You've been hearing in the news about OSB lumber is the #1 construction material and housing in North America. And we've heard all these things about, in Hurricane Katrina, the formaldehyde off-gassing, lumber liquidators, and all the formaldehyde coming up with that. And so what we've done is we came up with a technology in which we've just done a 70-ton pilot scale run in Canada of OSB lumber that outperforms industry standard in performance and cost without a drop of formaldehyde, without a drop of MDI, completely non-toxic green chemistry technology. We're super excited about this. Hair color restoration, believe it or not, this guy I went to UMass with, he was a professor at UMass with me in the biology department. And what he studied was how bugs break their exoskeleton. And after they break their exoskeleton, slowly it turns hard and black. So here's something in nature that goes from white to black. I don't know why I'm thinking this way, but I'm looking at that and I go, huh, that's kind of interesting. I wonder, men's hair coloring products, so everybody's hair coloring products, pretty nasty toxic stuff. Okay, if there's a lot of issues. Do you know that the men's product there, the key ingredient is lead tetraacetate? You can't sell a house in North America that has lead paint, but you can pour it on your head. And so I said, wait a minute. So I looked at it and I found that it's a tyrosinase cascade. I looked at the biochemistry. I didn't grind up bugs, okay? What I did was I took these materials and I mimicked it. And I got some gray hair. I put it in the beaker and it colored. Wow, this works. But it was dark, it was light, it was medium, it was all different colors. So I called the vendor and they said to me, oh, John, that's not one person's hair. That's a bunch of people's hair. Ooh. So I said, okay, I'm the grayest person in the building. I got complete gray hair, all right? I jump in the seat, I say, hit me. My hair goes back to the color it was 30 years ago. We have someone who had black hair that went gray. Hit her. It turns black. Someone with medium brown. This is not a hair coloring system. It is a hair color restoration. It puts back the hair color that you have. You have no choice. You're not picking a color. It puts the human pigment back. There's nothing artificial. If you were to take a snippet of my hair and compare it to 30 years ago, it is the exact same chemistry. What I've found is a way of penetrating these materials that allow the hair to take over. What I found is that our color hair, we have all the same molecules. It's the protein in our hair templates the three-dimensional packing of those pigments, non-covalent derivatization. And by getting the chemicals in the hair, it takes over where nature left off and you get the same color. This 16 months after inventing it, we licensed to a company. It's now on sale called Hairprint. If you go to myhairprint.com for $39.99 and act now, you'll get a Ginsu knife. You can get this color restoration. It's permanent, okay? So it won't wash out. It won't fade. It'll grow out. You'll get roots, but it's an interesting product, completely non-toxic. The people from Hairprint go on these trade shows and they eat the stuff while they're putting it on their hair. Now, I don't recommend you do that. You'll probably live, but you won't have a very good day the next day, so don't eat it. But it is non-toxic, okay? Here's another weird story. Do you know the show Whale Wars? Okay? Last year, I was on the center stage of the United Nations General Assembly. There's the big head there, he's up there. Now, why was I doing this? This show Whale Wars called me up one day. It's this show where these intrepid ship goes and chases evil, bad fisher people doing evil, bad things in international waters. They call the Coast Guard, and the Coast Guard swoops in. Well, they found this ship that was using a hugely illegal gill net. It's a big net that has little spikes, and it drags along the floor, and it's just terrible. And they dug up 75 tons of this gill net. They called me up, and they said, okay, John, we need this really fast. We got 2 weeks. And they sent it to me. And I took the gill net, we separated the nylon from the polypropylene, pulled out the pigment, unwoven, took out the lead, ground it up and extruded it. We didn't have the extruder that they needed, so we built the extruder, did a whole bunch of filament, sent it to Adidas, and standing next to me on the center stage of the United Nations, a dude from the board of directors of Adidas holding up the 2016 model running shoe made from ocean plastics. So we're the ones that made the filament for doing that and designed the process for taking nasty, ocean trash and turning it into something usable. Electronics and recycling. EPA regulated that the orange oil is a skin irritant. So a lot of products had to start backing out, not using limonene. And so the orange growers said, John, we need to have a better way of something to do with this. And so I can't explain why I think of these things, but I took limonene, hydrolyzed it to a 50% mixture, put it in with water, made a froth, took a lithium cobalt battery, ground it up, and found that I could float the lithium cobalt to the top, skim it off, and get 100% recovery of the lithium cobalt from the battery using not kerosene, not these organic solvents, but an aqueous mix of limonene, limonol to separate it out and recalcinate it to 100% recovery. We've got pilot scale tests going along in a couple different countries. We have a water harvesting technology where we have this technology that in the dark, the film is hydrophobic, in the light is hydrophilic. Now this is a super over simplification, but imagine I got a rowboat in the ocean. You get an umbrella. The underside of the umbrella has this coating. When the sun is up, water absorbs on the umbrella. When the sun goes down, it rains pure water in the rowboat. So you've got this desalination process that goes really slow by the function of the sun, or super fast in the millisecond time frame in the shadow of a windmill. Okay, so there's a handful of technologies. Now remember, this is all done in the last 3 years by 20 people doing about 20% of their time. Okay, so we're being pretty, and the one that's most relevant to today's meeting, remember I was at Polaroid. I spent 10 years at Polaroid. This is the world's first photograph, okay? This photograph was taken in 1825. Right? It was in France by a guy named Joseph Niepce, okay? And what he did was he took this material, put it on a sheet, and he made this picture. Do you know what the material was? Asphalt. The world's first photograph was made of asphalt. He discovered that sunlight and air oxidize asphalt, making it brittle so that you could wash it off, and wherever the sunlight hit, you would make a photographic image. So when I learned about your industry, and I have this friend, his name is Wala Morgera down at UMass Dartmouth. I was a UMass faculty. I knew him. He explained this to me. I go, wait a minute. So you've got this problem with oxidation happening with things, and well, this has been known for 150, 160 years in photography. Huh. Now, full stop, my Alzheimer's drug. The way the Alzheimer's drug works, okay, is I found out that in the brain, you've got these proteins that bind inorganic substrates, all right? And the organic polymer wraps around the inorganic substrate, and it aggregates. And that's what causes Alzheimer's. So I came up with this small molecule that slips in between the inorganic-organic phase and controls the disaggregation. And that's how the Alzheimer's drug works. So, what is asphalt? Asphalt, when the sun and the air hit it, what happens is it oxidizes on the surface, and we dig it up, we take it off, and we repave it. I realized that in the same way that I had the Alzheimer's drug, if I took a molecule that had two parts to it, one part compatibilized the asphalt, and the other part bound to the aggregate, what I could do is I put this in, pull it in, separate off the oxidized form, mix it up, reverse that oxidation, turn it around, have it back bind to the inorganic particle, and make an even better coating afterwards. And so what we did is on November 25th, 2013, we dug up my driveway. Now, this is much to the horror of my wife. This was 3 days before Thanksgiving, and I dug up my driveway, and we're going to try this out. Okay, and so we've got it, and we get it contracted, and we got these two dump trucks come with the asphalt. Now, they're laughing at me. They're saying, John, you are insane. It's 17 degrees Fahrenheit. We never pave at 17 degrees Fahrenheit. You're putting in over 60% recycled content. What's going to happen? Just going to tell you, we're going to open up this truck, big hockey puck's going to fall, it's going to go in your front yard, and we're driving away. Okay. They open it up, comes out beautifully. That was 2013. This is a couple days ago. The driveway is perfect. So we started a company called Collaborative Aggregates, non-covalent derivatization, collaborations, you get the picture here. Because I'm a thermodynamic nerd, we called it Delta S, which is the thermodynamic symbol for entropy. And this thing has been on the market now for quite a while. And so there's Delta S and there's EcoSail. Now, I am the scientist that worked on inventing it. I'm not the marketing person. Pete Montenegro in the back knows the business of it, so I can't answer any questions about the business. But if anyone's interested in it, and I know that there's a booth up there. But my point here is that innovation creativity is kind of a funny thing. When people hear about green chemistry, go, oh my God, this is going to be all kind of put handcuffs on us, slow us down, make it really hard. I would argue that we've had a pretty good success rate. We're not any smarter, any better than any other group of people. And we're not successful in spite of green chemistry. We're successful because of it. And here's what I mean. Necessity is the mother of invention. If you had a group of scientists and said you can only work with molecules that start with the letter D, well, that'd be kind of silly, but it would force people to think differently. And they would come up with different answers. Well, what better way to think differently is that you have to think about environment, health, and safety. And instead of it being a roadblock and slowing it down, if everyone else is reading the same journals, reading the same textbooks, taking the same class, doing the same thing, well, guess what? They're going to end up with the same results. If you approach a problem from a different perspective, from the toxicity, environmental impact, it doesn't slow you down. It speeds you up and puts you in a space that other people aren't at. And that's the opportunity here. There is clearly a moral and ethical component to this. But I would argue this is faster time to market, economically, hands down, the way to go as well, if done correctly. And that's my story, and I'm going to stick to it. Thanks. I'm done. Thank you. Yeah.